Good day, everybody. This is Chris back again with the Ancient Scholar, and this is going to be part 2 in the series on the volume of distribution. Okay, so let's pick up where we left off. So where we left off is we talked about body water, and we said that in a healthy 70 kilogram patient, approximately 60% of that patient's weight will be water. And so 0.6 times 70 gives us about 40. It's actually 42 liters. Well, we just went ahead and simplified it, made it 40. And so we conceptualized the human as being a bag or a container of water that contains 40 liters. And then we worked through an example and we said, hey, let's say that we gave 100 milligrams of a medication IV, and so we essentially bypassed the absorption phase and just dissolved 100 milligrams of that in this 40 liters of water. And when we did that, we went ahead and gave it, and then we calculated the concentration. So we took a small sample of this, and we calculated the concentration, and we got a concentration of 2.5 milligrams per liter. It actually says milliliter there, but let's just go ahead and change that real quick. So we got 200 milligrams per liter. All right. So 2.5 milligrams per liter, and then we went ahead and divided this out, and the milligrams canceled out, liters is left behind, and then that gave us 40 liters. And that's more or less what we'd expect, right? If I evenly dissolved 100 milligrams of something in 40 liters of water, I would expect a volume of distribution of 40, right? Because it's evenly distributed throughout that whole 40 liters. So now what I want to do is I want to give you guys a couple of examples. So let's say that we now have example A here. And we take 100 milligrams of some substance, some drug. We inject it, we give it via IV push, IV bolus, and we allow it to get into the central circulation, and then we go ahead and we check the plasma concentration. And so in this case, I get a plasma concentration of 0.25 milligrams per liter. So we go ahead and plug that into our formula. The parent volume distribution is the dose divided by the concentration, and so 100 milligrams divided by 0.25 milligrams, the milligrams cancel out, liters falls out of it, 0.25 goes into 100 about 400 times, okay? So that gives us a volume of distribution of 400 liters, and this is where things start getting rather non-intuitive. So hopefully you can see where we got this, okay, that where we got this from this formula here, from calculating this. But if I am to believe this, if I'm to take this value literally, then the interpretation is that this this 100 milligrams is not dissolved in 40 liters, as is the case here, but somehow this drug is dissolved in 400 liters. Well, clearly that can't be the case in a literal sense because we only have 40 liters to deal with. So what's going on there? And what's going on is the volume of distribution is not taken literally, and this is why I've been calling it the apparent volume of distribution, because it appears as though this 100 milligrams is dissolved in 400 liters. That is to say that to get this low concentration here, such a low concentration, I would have to dissolve 100 milligrams in 400 liters of the plasma, of water in the plasma, to get such a small concentration. So what does that mean? Well, what that means is clearly we don't have 400 liters, but what can happen is, and let's just kind of work this out here. So let's say, okay, so I'm going to take situation A here, and we're going to conceptualize this. So I put 100 milligrams in. Okay. Now we know that the water just isn't floating inside of a bag of flesh willy-nilly, that there are several compartments contained within the 40 liters of body water that we have. And some of the major compartments include the fatty compartment here, okay, include the blood plasma here, and then within the blood we have lots of proteins, and the most common protein is albumin, and so I kind of have all of my blood proteins here. Now remember, when we actually measure the concentration of the blood, we're not measuring it in all of these individual compartments, but rather we are only measuring the concentration of the drug here in the plasma compartment. And so what can happen here is, let's say that I give 100 milligrams of that drug, and that drug is very, very lipophilic. And so what's going to happen is that drug is going to be sequestered. It's going to be very concentrated in the lipid or the fatty areas of the body, and it's going to be less concentrated in these other areas of the body. And so what's going to happen is, when I measure and I take a small volume and I measure the concentration of the blood plasma, the concentration is going to appear to be very low. It'll appear to be very low because the drug is not actually in the plasma, right? It's not actually there. Rather, it is actually sequestered in the fatty compartment. So the concentration in the plasma is not necessarily indicative of the entire body, right? And so what we get is, when we calculate this, we get a volume of distribution that is very large, right? It appears as though that 100 milligrams, if I forget about individual compartments, it appears as though that 100 milligrams is dissolved in 400 liters, and it's not literally dissolved in 400 liters. It just appears that way, and we know that it's actually sequestered in some other compartment that we're actually not able to directly measure. And then kind of the opposite happens. So let's now look at situation B here. So let's say that I give a dose of 100 milligrams of drug B, and then I measure the plasma concentration, and it's 10 milligrams per liter. All right, so I go 100 milligrams divided by 10 milligrams, okay, and then that gives me an apparent volume of distribution of 10 liters, right? So in this case, I have a kind of a different situation here. So I give 100 milligrams of that drug, and that drug, okay, instead of being spread out, and going into the fatty space, instead it gets sequestered. All right, the lower it gets here, the lower the value, the more protein binding we get. Okay, the more attracted we get to the proteins. Okay, to the albumin, for example. Okay, so it kind of gets sequestered within the vascular compartment. We get a little bit of it in the fat, okay, but it remains highly sequestered within the vascular compartment, and so the concentration, right, when we measure it, when we take a sample, all right, of the blood, and remember the blood, is not only the plasma, but it contains, the proteins as well. So when I take a sample of blood and I test the concentration in the plasma, the concentration is going to be very large, and it will appear as though that drug is dissolved in a smaller volume, right? Because it is more concentrated in this area and less concentrated over here. And so what we get, the interpretation of the volume of distribution, is a volume of distribution of around 40 liters, right? When I calculate my volume of distribution, if it's around 40 liters, that means it's fairly even in its distribution. So it's fairly evenly distributed, throughout the body, in the fats and the protein binding and the blood plasma and other tissues. And then the smaller I get up here, okay, so 40, 30, 20, 10, 5, 1, 0.1, and so on, right? The more protein bound it becomes as a concentration increases that we measure. And then the larger the apparent volume of distribution gets, okay? So 40, 50, 60, 70, 80, 90, 100, the more lipid or fat bound, that is to say that the drug is being more and more sequestered in the fatty compartments. And so we have a much more dilute plasma concentration. And so that's what we call the apparent volume of distribution, because it appears as though it's dissolving in a certain volume. And that's simply due to the fact that we're only able to assess the blood, right? We're taking a sample of blood and we're not assessing, the concentration directly in other areas of the body. And so we have to interpret the volume of distribution appropriately. So now what I want to do is I want to give you guys just a couple examples here. Okay, so I've drawn this, and occasionally what you'll see done is you will have the literal volume of distribution, and then occasionally what will happen, and I see this a lot in textbooks, is that they will divide the volume of distribution by body weight, right? So they'll calculate the volume of distribution and divide it by 70 kilograms, right, or a generic 70 kilogram patient, and we will get a value in liters per kilogram. So what I have done is, in this column here is the actual volume of distribution, and then in this column here is the equivalent of that volume of distribution divided by 70. So, for example, a volume of distribution of 1 liter would equal 0.014 liters per kilogram, okay? Those are equivalent statements, just like a volume of distribution of 100,000 liters is equivalent to 1,429 liters per kilogram approximately. Okay, and then I've drawn in here, all right, so right in here, okay, volumes of distribution that float, 25, 30, 40, right in here are drugs that tend to be fairly evenly distributed throughout the body water, okay, throughout the body. And then the smaller I get, the more protein binding I get. And then the larger I get, the more fat sequestration we get of that particular drug. And then what I'd like to do is just give you guys a couple of examples to solidify this, and then hopefully it'll make sense. So the drug warfarin or Coumadin has an apparent volume of distribution of 8 liters, and that is equivalent to 0.114 liters per kilogram approximately. All right, so that is going to be right up in here, which means warfarin experiences fairly substantial protein binding. Okay, and then another drug is ethanol, right? This is drinking alcohol, ETOH, ethanol, and it has an apparent volume of distribution of about 30 liters, and that would be about 0.429 liters per kilogram approximately. And so what does that tell us about ethanol? Well, that tells us ethanol is, when you drink alcohol, it actually distributes itself fairly evenly throughout all the water in your body, right? The closer you get to the actual value of total body water, 40 liters, the more evenly distributed throughout the body water that drug is. And then let's do delta 9 tetrahydrocannabidiol, or THC. That is the psychoactive component of marijuana. And this has a volume of distribution of 448 liters. In some cases, a volume of distribution of THC changes somewhat, but in some cases it will have a volume of distribution of 448 liters in people that smoke a fair amount, and so we'll just assume that's the case, and that gives us a 6.4 approximately liters per kilogram. All right, so where is that going to be? What are we looking at here? Well, we're looking at right in here, right? 448, so it's greater than 100, and so that tells us that THC tends to be sequestered more in the fatty compartments. It's much more lipophilic in that sense. And so this gives us a good idea of when we look the volume of distribution up for a drug, it gives us an idea of how the drug's distributing throughout your body and where is it going. Is it distributing it out equally? Is it wanting to stay more in the blood because it's binding to proteins in the blood? Is it distributing it out into the fatty compartments rather? And then that helps us determine the best dose, right? We can do a dose response curve, and we can find out what concentration of plasma is associated with a certain physiological response, and the volume of distribution helps out because we may need to give larger doses of certain medications if they experience significant, say, protein binding. We may have to take that into consideration, that a large part of that drug will bind to proteins, and it may not be available to interact with receptors in tissues in other areas of the body, or perhaps that drug is sequestered in fatty tissues. Or perhaps we might have to give a lower dose because it's a drug that works in fatty tissues like the brain, right? The brain is very fatty. It's part of your fatty compartment. So if you have a highly lipophilic drug that stays in the fatty compartment, you might need to give a smaller dose because it will tend to stay in the brain and it will tend to have a prolonged duration of action, those kinds of things. And so hopefully you can see how the apparent volume of distribution can be helpful pharmacologically. Okay, hopefully that made sense, guys, and hopefully you found this video helpful. As always, thanks for hanging in there.